Yeah, so not in Paris anymore. I'm now at JILA. Actually, the experiment that Martin mentioned, it was mostly measured by Cyprien Dijks, who's really a brilliant PhD in Paris. But I'm now working in on the KRB experiment in JILA with Junyi. And today I'll be telling you about our progress towards a 2D degenerate Fermi gas of polar molecules in a single layer. So I think we'll see many variations of this slide during this conference. I don't have to explain to you why molecules are interesting because of their rich internal structure and dipole-dipole interactions. And also not that ultracold molecules have been used to study ultracold chemistry, many-body physics, and recently also quantum information. But I will be focusing on the many-body physics side of things, and particularly these quantum magnetism spin models, which connects to high TC superconductivity and can also be used to generate spin squeezed states. So how do we create those models in the lab, those systems in the lab? Well, we use ultracold KRB, and we encode we encode a spin onto the first two rotational states of KRB, which has a splitting of about 2.2 gigahertz. We load them into a lattice, which, of course, we can tune the tunneling rate depending on the intensity of the beams used. And then we use the dipole-dipole interactions to generate strong dipolar interactions that can be of nearest neighbor or even next nearest neighbor length scales. So these are strong interactions, they are long range, they're anisotropic and tunable with electric fields, external fields. And so to dig a little bit deeper into these dipole-dipole interactions, as I said, we have a spin encoded onto the rotational states. So we have, if we look at the interactions between two molecules, we have a spin up or a spin down. So we can get 4 different compositions. So this leads to this 4x4 matrix with this geometric term over there. And so to dig a bit into this matrix, what we have here is we have the interaction between the down-down, between the up-up, the down and the up. And then we also have this exchange interaction, which leads to these off-diagonal terms in the matrix. And we can rewrite that a little bit in terms of these J, Z, V, and W terms, which I'll show in a bit, because if we load these molecules into a lattice and allow tunable tunneling, we'll get this so-called TJVW model. So it's a bit intimidating maybe, but it's just a rewrite of all these terms together with the tunneling. So we have the tunneling over here, we have the spin exchange term over here, then we have a Ising term, a density-density term, and a density spin term. And we can tune these interactions using external fields, both DC fields, electric fields, and microwave pulses. And so just to give you an example, just to give you an intuition, if we tune it with DC electric fields, we have these JZ and J perp, so the spin exchange and the Ising terms, which are just these rewrites of these matrix elements that vary with electric field as a function of electric field. And we can also parameterize this with this anisotropy parameter chi, which is just the difference between JZ and J perp. And just to give an example, because there's many Hamiltonians that we can generate with this, but just to give you an example, here you have this point where chi equals 0. This is the Heisenberg point. And we can create, if we pin the molecules so don't allow tunneling, we can create this XXX Hamiltonian, just to give you an example. We can also tune these dipole-dipole interactions using Floquet engineering. And the way you should see this here is we use microwave pulses to essentially stroboscopically rotate the Bloch sphere as the system evolves. And we have a little bit more freedom then to generate kind of effective Hamiltonians, such as a 1-axis twisting or a 2-axis twisting Hamiltonian, which can be used for spin squeezing. And just to show some recent results from the KRB lab, this is from before I joined, They studied spin dynamics in the TJ model, so this is the model that I just described, and varied just the tunneling rates and also this anisotropy parameter chi, and studied the density-dependent contrast decay in Ramsey contrast experiments. I don't have time to explain this in detail. Another recent study was on this Floquet engineering, where they generated one-axis twisting and two-axis twisting Hamiltonians using this Floquet engineering, and tracked the evolution of the collective Bloch vector on the Bloch sphere. But all these experiments were done in a 3D lattice at about 13% filling, or a stack of 2D pancakes at relatively low densities. So what we want to do now is we want to really bring this into the degenerate regime. Oh yeah, and we could select like the different layers using RF spectroscopy, using an electric field gradient. But if we really want to bring these experiments into the degenerate regime, we want to get higher densities. And we really want to bring the system into a single 2D layer, because then we get full control over the anisotropic interactions using the angle of the electric field. We can compress all the density into a single layer, which means that we have a higher density, a higher TF, so a lower T over TF, which allows us to see novel quantum phases in this TJVW model. But the challenge is compressing things is difficult. We get adiabatic and non-adiabatic heating, and we get 3 body losses during compression. But okay, we do it anyway. And so the way we do it is we start with an atomic mixture, because this is a mixture of K and Rb atoms in a crossed optical dipole trap. Then we load in a large spacing accordion lattice at spacing of 14 microns, and we compress down to 2.8 micron spacing. And after that compression, the Rb, which is bosons, is small enough to be fully loaded into a single layer of this 540 nanometer spacing vertical fixed spacing vertical lattice. So how do we create this accordion lattice? Well, we took some inspiration from the Greiner lab. We have this dovetail prism over here and a rotatable mirror. So, and depending on the angle at which we hit this lens, the interference pattern at the end will either be give a large spacing or a small spacing. So this is the way we compress. And what we want to do is we want to make sure that this central layer actually stays in the center. So we have some phase control for that. And just to show you that, let's say we load the atomic mixture in the center of this layer indicated by the yellow arrow, and we compress it down to 2.8 micron spacing. We see that indeed this is passive phase stabilization, that it works pretty well. So we can try in this accordion lattice. So now without transferring it to this vertical fixed spacing lattice, we can try to make some molecules. So first thing we tried is we directly load from the cross optical dipole trap this accordion lattice at the smallest possible spacing. And we get multiple layers, as you can see in the top image over here. But if we now load at 14 micron spacing over here, and we compress it down to 2.8, you see that we nicely get a single layer, and the OD is much higher. And this is the preliminary results that of the best conditions that we got in this accordion lattice. So we now have 50,000 KRB stars, so that's Feshbach molecules. If we have a stirrup efficiency at zero field of about 90%, so you could see this as like 45,000 ground state molecules in a single layer of this accordion lattice at about 310 nanokelvin, which would give a T over TF of 0.7, which we're very happy with. It's not the best conditions that we could generate in 3D, because in 3D, if we directly make the molecules in the crossed optical dipole trap, we would be able to get results like this. But of course, this is without this compression that we did. But the thing is, we're not fully 2D yet, because the temperature is about 0.6 h bar omega vertical. So we need to compress a little bit further, or yeah. And that's why we load into this fixed spacing lattice with 540 nanometer spacing. And then we can generate the molecules there. So we do this loading of the vertical lattice, this fixed spacing lattice, again on the atomic mixture. We can create the molecules there at a non-zero electric field, and we can start dipolar evaporation in this single 2D plane. So the way that works is we have we start out with a homogeneous electric field and a dipole trap, and then we ramp on the voltage on these rods. So we parameterize this by this gamma. So we ramp on that voltage, and that creates, instead of having only this optical potential trapping you and then a flat electric potential, we generate an anti-trapping curvature on the electric field, which gives an effective lower trap depth, and that allows us to evaporate. And this has been done in multiple layers already before, where they were able to reach a T over the F of about 0.6. But we want to do it for a single layer. So let's do that. So we start that procedure on our molecules in a single layer. And this is our recent result. So we start out here with about 4,000 molecules now, ground state molecules, and we evaporate down to about 55-ish nanokelvin. And you can see that the evaporation efficiency, which when it's lower than 2 in 2D, this is efficient evaporation, that the evaporation is pretty efficient. It's not super great yet, because if we plot it as T over TF, and now this is TF is the 2D TF of the trap, we see that this step is not that efficient, but we are now touching degeneracy in a single layer. So we're almost there. Yeah, so then we can start thinking about what to do in this DJVW model. And there are some interesting phases that have been predicted. I don't have the time to go into detail, but essentially, as a function of lattice filling, we expect to see a phase transition in which there, from the Ramsey contrast decay, we will be able to see directly that the molecules essentially start rotating in a kind of phase-locked way. This is predicted, which is predicted just for pinned molecules already, but itineracy may help. And as I mentioned, we might be able to see some spin squeezing as well. So I'm out of time. And so with that, I would like to thank the team, of course, the PI, Junyi, and the current team members, Annie, Junyu, and Phil, and Cal, who is finishing his PhD soon, and of course, the theory collaborators, and you for your attention.
Thanks for a great talk, Tim. Are there any questions? Not, I'll start. So I was just wondering, at the very end, you're talking again about rotation, but you also have like this electric field polarizing the molecules, and that same electric field also determines the trap, right? So what actually happens between...
So what we do here is...
between evaporation and here, I guess.
Oh, yeah, so what we do here is, well, basically the dipolar evaporation, it happens just in the 0, 0. And then, in principle, what we do is we do a pi half pulse. So now the collective Bloch vector is in the equatorial plane of the Bloch sphere, or at some angle we can do all of it. And then it just starts processing due to the evolution of the dipolar dynamics around some axes given by the Hamiltonian, essentially. So for instance, if you have a one-axis twisting, there it's, if you look at it in a mean field way, it's like Larmor precession. But then the field is given by the size of the SZ, the mean field SZ. So that's a way of looking at it.
Sorry, but I guess my question, this is all with electric field on still?
Yeah, this is all with electric field on.
Thanks. Thanks for clarifying. Are there any other questions? If not, let's thank Tim again. in there.